presentation is about Bayesian weighted information measure. Actually, in this presentation, we start with some introduction, some useful notion that we need to know for the beginning, and then the chain rule, and then in the next part we go to weighted pullback measure. We introduce or present actual information, and then the application for the weighted part, for the normal distribution. And then weighted analysis, actually Bayesian analysis, I introduce Bayesian weighted information measure, and then at the end, the application part. Let me to introduce first pullback information. Let X and Y be two random variables with support as having density function fx square x and distribution function fx square x. That these two random variables, they can describe any real situation. The pullback information measure, as we all know, it can be known as relative entropy pullback divergence. It's defined like this. So integration logarithm fx and gx dfx. And we all know that in statistics, this measure is to describe the differences between two distribution functions, and it should satisfy in three properties: self-similarity, self-identification, and positivity. As we all know, the information describes the difference between two distribution functions. It's not to tell which of this distribution has more information. It's just the difference between two distribution functions. In 1941, Pullback and EBEB, they described, actually they introduced information, and they say, okay, we can have the information of the distribution function if we have the pullback information between that distribution function and the uniform case. Let me to define another concept, which is entropy. Researchers that work on this field, they are completely familiar with this. Consider x is a continuous random variable, then we define hx minus expectation logarithm x as entropy. And if you want to extend this definition for the vector x and y, and which they have joint probability fx and y and conditional probability fy given x, then the joint entropy is the expectation logarithm f joint distribution, probability function, and the conditional entropy is the expectation of logarithm fx given y. But of course, Cover with his co-author in 2006 showed that there is a relationship between conditional entropy and joint entropy, which you can see here. But the point is that, okay, so if we have one observation and we want to find the information provided by that observation, we can compute the differences between entropy and the conditional entropy, or we can compute the pullback information between fx given y and fx. Another definition which is quite interesting here, and we need it, is expectation information or mutual information. If we have the expectation of difference hx minus hx given y, then we have the mutual information. Or if we have the expectation of the information between marginal distribution and the conditional distribution, then we have mutual information. Which actually mutual information is defined, the information, the distance between a distribution function when they are dependent with distribution function when they are independent. Another concept that we need to know is weighted entropy. What is weighted entropy? If you consider the occurrence of one event, it has two parts, the quantity part and the quality part. The quantity part is related to the probability, and the quality part is related to the utility. For example, in communication engineering, if we consider a signal as a random variable, it has two parts, the quality part and the quantity part, which we can compute the quantity part with probability and the quality with the utility. But we should consider that the utility part is independent of probability, and in this situation, the information should be a function between probability and actually with respect to probability and utility. So, Bayes with his co-author in 1984, they actually introduced weighted entropy. In this sense that if for an experiment with finite measurable partition A1 until An, with probability P1 until Pn and utility set U1 until Un, then we can have the discrete case, this definition for the weighted entropy, and the continuous case, this definition of entropy. So what is the difference between weighted entropy and entropy? The difference is that in entropy, we compute the entropy based on the probability. But for the weighted entropy, we consider the value of random variable also. So it's quite interesting. Okay, another definition is generalized weighted entropy. If we replace x with a function of phi x here, that phi should be positive, then we can have the generalized weighted entropy. Of course, we can find some results about this, but because of the time, I cannot go on to be precise for this definition. Based on this, I define the actually weighted join entropy. As you can see, just we have x, y here, and the conditional one. We have x, y here in the conditional case. In 2006, Dickerson actually, they gave a proposition. What this proposition says? This proposition says that the weighted join entropy is, actually there is this relationship between weighted entropy for x and y and weighted join entropy. And, okay, so up to now, we know whatever we need to know. Now the point is that we have chain rule for entropy. The question is, do we have chain rule for the weighted entropy? We have, but it's quite similar. Assume that xy is a pair of non-negative random variables. Then we can have this relationship between weighted join entropy and weighted conditional entropy. In this case, it should be x expectation y given x. And equivalently, we can have this relationship, which is just changing between x and y, switching. Okay, so we have weighted entropy, we have pullback information. Can it be described, or is it any concept related to weighted pullback information? Yeah. Actually, it was quite in the same period, in 1986, if I'm not right. This weighted pullback information was defined for n events E1 until En, F1 until Fn with probability P1 until Pn and Q, and so on. We can see that this is the definition of weighted pullback information. And then in continuous case, then we can define this weighted pullback information. And of course, with respect to what we have now, we can define weighted mutual information, which is here. Just we have x, y here. Okay, so I want to see that if we define weighted mutual information, can we have a relationship between weighted entropy and mutual information? We have this relationship between weighted mutual information and weighted entropy. But the point, this idea comes from this expression that we can find for the weighted mutual information. And then then, of course, we can extend these results and have this relationship, which is the weighted, generalized weighted entropy for X or Y, and then we just need to pick, let's say, the part of weighted joint information. Please note that phi X is X expectation Y given X, and phi 2Y is this expression. And based on this, the point is that, okay, now we have marginal distribution. We have conditional distribution. What is the weighted information between both of them? We can compute it based on this relation. And of course, we can compute the mutual weighted information based on expectation of weighted information between X and X given Y. But these all are theoretical part. How we can use them? First, I give you one example that shows, okay, whatever we could gain theoretically, we can see it actually in the normal distribution. If you consider the famous standard normal distribution, and they have, of course, we all know this is the distribution function of joint normal vector, and then, okay, we all know that X given Y has this normal distribution. In general, we can compute the entropy for any normal distribution in mu and Ryan-Sick model with this expression. Then, of course, we can have the conditional one. This all computation, we arrive to this part. This is not, let me bold this point, that this is not weighted. This is the pullback. We all know, and they work a lot about pullback. We want to see what is the difference between pullback and weighted pullback. This is the point. So, we have here with fx, fx given y. And as you can see in this figure, as rho, is increasing, the information between fx given y is increasing. If you want to be more precise and to understand better, you can see here, and this is obvious actually, when the dependence, the correlation between x and y is increasing, it means that fx gets far from fx given y, which this distance is big. When this distance is big, which means it has more information. But do we have the same result for the weighted one? For the weighted one, we started to compute. This is the weighted entropy. Then we have weighted entropy in conditional case, which is the interesting part is that this rule is just for normal. For normal case, the weighted entropy is actually connected with the entropy with expectation. And then with some computation, we arrive to this point. So, for the normal distribution, weighted pullback between fx given y is like this. If we see in this figure, there's a difference. Let me tell you that first, pullback information should be positive always, but weighted pullback information, there's no guarantee which is positive. In this case, you can see that it can be negative also. If you want to be more precise here, let's concentrate on the positive part. When y is positive, we can see when rho is increasing, then the weighted pullback also is increasing. But when rho, in this case, is negative and it's increasing, the weighted pullback is decreasing. This is actually exactly coincide with our expectation because it's related to the value of x. So when the rho is increasing in positive part, it means that they are going far. When it's increasing in negative part, it means that they are going less. But in absolute value, in any case, the information is increasing when rho increasing. Okay, we have this all, but can we use it in another sense? We can use it in Bayesian analysis because we have here the conditional. Then it came to my mind, okay, we have a marginal one and the conditional one. So we can have the weighted pullback information between posterior and prior distribution. So, as we all know, if we have a random variable y, and then this is the posterior distribution function, and this is the predictive distribution, which can be defined like this. So, let me define, give you another definition. This definition is expected weighted information. Actually, it considers a kind of average of weighted pullback between prior and posterior. So in this case, please note that phi prime theta is theta f theta given y, and f theta and phi theta is theta expectation y given y. And we can have this definition, this relation, as we saw for the condition. It's the same, just considering in Bayesian analysis and prior and posterior. The point is that how we can use it. The nice application we can use in selecting our models. In selecting models, for example, if you consider Weibel family. In Weibel family, if y given theta, if we define in this way, we can have the gamma prior, and then we can have this posterior. So, for the pullback information, we have this computation, h theta given y, and then we have this pullback. If we consider this figure, this is the expression that we could find for the pullback information between prior and posterior. So we have this point. As you can see, when c is increasing, for a fixed y, the information is increasing. So this measure is not going to be a nice measure, because we can choose big C and we have more information. So this is not helpful, useful for choosing a model. As you can see here also, for example, for given y5, if we consider C equal to 10, we have maximum information. But can we use for the weighted pullback can be a nice tool to select a model? The answer is fortunately yes. If we consider H weighted entropy, we can compute this expression, and at the end we have this big expression for weighted between posterior and prior distribution. And the nice part is, as you can see in the figures, it's not monotonic. Sometimes it's increasing, sometimes it's decreasing. Or if you want to be precise, for example, if y, the observation of y is 5, c is equal to 3, as maximum, in this case, in participant case, as maximum weighted information. But when it's half, the c equal 10 is maximum weighted information. So based on given y, we can have different c. So we can select a nice Weibel distribution. So in this case, we can say that actually weighted pullback can be a nice method for choosing actually a nice Weibel model. This is just the beginning of idea, and actually, as you can see, it's about uniform case. What is I'm questioning now, I'm going to work on is the multivariate case, because it's more interesting. And then in multi-parameter case, because as you see, they are uni-parameter models. So this is the idea, and I guess in this case, we can, since weighted pullback information is related to the value of the parameter, so we can say it can be a nice measure for selecting models. Thank you very much.